All right, let's start today's session. So what we are going to do is, we are done with chapter 3. We're going to start discussing time response. Chapter itself would be time response. We will discuss first and second order system. Okay. All right. So if you're looking at what time response is, I explained to you. We did a little bit of time response when we were doing that experiment, right? So you have, until now you have modeled system model. So we have looked at transfer function model, okay? And we have looked at state space model, right? So if you look at what is transfer function is generally you use this G of S is equal to C of S divided by R of S, right? Here, G of S is transfer function, C of S is the response, and R of S is the input. So if you do this, C of S, you take this, you do G of S into R of S, okay? And then Laplace inverse of C of S, you're going to get C of T. This is typically called the time response. If you're looking at, if you plot this,
basic words, the time response is the Laplace of the output. Isn't transfer output of input?
Huh?
Isn't transfer function output of input?
Laplace inverse.
That's the time response.
So if you have, this is time, and this is C of T. Okay. So whatever, as time progresses, if you plot the response, how the response varies, that's the time response. Okay. So when we are looking at time response, this is the general understanding, general description of time response. Okay, this is the mathematically this is what you get. So if you, when you do this, what is this G of S? It's one polynomial over the other, right? You have looked at this. So if you take that polynomial, you multiply that by a given R of S, known R of S, and then once you've done that, you take the inverse of that polynomial. You're going to get the time response. What would this C of S be? Just C of S would be, what response is this? What kind of response is this? What form of response is this?
Output?
Huh? That's frequency response.
Oh.
Because it's a function of S, which is S is a frequency gradient. Okay? So this is frequency response, this is time response.
One more time, that's a frequency response because of what?
This give me
Oh, the S.
S.
Okay. And then the T.
You have to define two things here. Poles and zeros of a transfer function. Okay. Let's discuss this in the context of an example. If G of S is equal to S plus 2 divided by S plus 5. Okay? This is the given system. This is your transfer function. And what is the order of this transfer function? First order. It's purely dependent on the denominator. Okay? Now what is, if G of S is this, the first thing would be, well, a simple question would be, find the response for a unit step input. Okay? So now what you're looking at is, for unit step input, R of S is equal to 1 over S. Okay? This is how R of S is defined. Unit step input. What is a unit step input? We have looked at this unit step input. Just for now, just think about it. R of S is equal to 1 over. Just take this for now. We'll discuss what this unit step input is. So what would be the response of this system now? Response C of S is simply equal to G of S into R of S. Okay, which is equal to S plus 2 divided by S into S plus 5. Fairly simple. Right? Now, what would be the time response of this system?
The inverse response of that whole thing.
Right. So time response would simply look something like. So what you'll do is you'll just split this into A over S plus B over S plus 5. Okay. You'll find values for A and B. And your time response will look something like this. C of T is equal to A, right, plus B e to the power of minus 5t. Okay. If you actually try to solve this is a partial fraction expansion. Okay. So if you actually solve for A and B, your A will turn out to be 2 over 5. Okay. And B will turn out to be 3 over 5. This would just simply be 2 over 5 plus 3 over 5 e to the power of minus 5. So just compare these two. This is frequency response, this is time response. Because everything here is expressed in terms of time. Everything here is expressed in terms of frequency. Okay? So if you plot this, if you do a plot of this, how will the plot look? What is the final value of this? Tell me. As time approaches infinity, what is the value of this?
Goes to zero.
Huh?
Goes to zero.
This term goes to 0, right? The second term goes to 0. But this term remains as
So it just stays.
2 over 5.
Goes to 2 over 5.
2 over 5. So if you look at this is t and this is your c of t, right? So we'll have marked this this 2 over 5. This is, let's say, 2 over 5. Okay? The maximum value would be, when time is 0, this will be 3 over 5. Right? Because e to the power of 0 is 1. So 3 over 5 plus 2 over 5 is 1.
What would the maximum time be when t is 0?
No, it starts at time 0.
Oh, okay.
We don't know negative time, right?
Okay. So that's the minimum time. The smallest.
Response, we are looking at response.
What's the maximum value?
Maximum value of the response as at t equal to 0. Here t is 0, right? And somewhere here t is infinity.
Okay.
This is the value of, this is t, response when t is infinity. Okay? What is the response when t equal to 0?
That's the 2.
1. Okay? 2 over 5 plus 3 over 5. Okay? So if you look at this, let's look at this as, this is your 1. So your response will looks like this.
It's decreasing so as.
Okay? It is an exponentially decaying system. If you look at it. This is 1, this is 2.
Yeah, that's what I was thinking.
Okay? If you look at, this is how your response is going to look. This is time response. Time response is a plot of the response as a function of time. Correct?
Okay.
So here in this system, poles for C of S equal to S plus 2 and S over divided by S over S plus 5. System is infinity at S equal to 0 and S equal to minus 1. Right? When S is equal to 0, what happens?
When s is equal to 0.
In that, think about that.
Well,
If you input S equal to 0, what happens?
that would be an issue because then you have 0 in the denominator.
That goes to infinity. So that's what I'm saying. System goes to infinity at S equal to 0. Correct? So what will happen is this will be 2 over 0. This S will
Make the whole thing.
go to infinity. Okay? What happens if S is equal to minus 5?
Yeah. I thought perhaps we're looking at it from the wrong mathematical point of view, but I thought when you have s in the denominator, that's actually impossible.
No, why is not? Why 0 frequency is not possible?
Can't divide. She's saying you can't divide by 0.
Yeah, so it's like undefined
It's not undefined.
in the calculator.
Don't go by the calculator.
So would we learn that?
I don't see any way you can make it.
It'll be two
Like, because you can't use those rule or anything like that.
I understand mathematically what makes the system go to infinity. What makes the response go to infinity? That's it. Don't confuse yourself with anything. Okay? What makes the system go to infinity? What value of S will make the system go to infinity? Make this equation go to infinity. If you are asked, your goal is make C of S equal to infinity, what value of S will you substitute?
Zero.
Huh? Not approaching 0. If you substitute S equal to 0, substitute S equal to 0 in that. What is the value of C of S?
That Clayton said 2 over 0.
So that's infinity. Anything over 0 is infinity. It's not undefined. Okay? 0 over 0 is undefined. Infinity over infinity is undefined. But anything over 0 is not undefined. It's infinity. You have to be clear about that. Because infinity itself is not defined.
Infinity itself is not defined.
Infinity is not defined. Infinity could be 2 million, infinity could be 3 billion.
Okay.
that's
That's
probably
not
right.
that's
Yeah.
But
definite.
something over 0 is infinity.
Yeah, undefined.
Okay? But infinity over something over 0 is not undefined. So keep that in your mind. Just because your calculator doesn't give it, it doesn't mean it's not defined. Alright? So what is the other value of S which will make it go to infinity? Negative 5. Right? So these values of S that cause the transfer function to become infinite are called poles. Okay? In other words, roots of the denominator are poles. Okay. So here what we do is, we don't generally take response, we look at the system poles. So you really have to look at G of S is equal to S plus 2, S plus 5. Let's just stick to this, okay, this definition. Values of S that cause the transfer function to become infinite are called poles.
What's that first word in parentheses?
Values of S,
He was talking about in parentheses, it's roots, right?
huh?
Roots.
Roots of the denominator. So what is the root of the denominator then?
Negative 5.
Negative 5 is the only root,
Oh, you
right?
took that S off?
Correct? What is the root of the numerator?
Negative 0.
Negative 2. That's simple. Okay? So what does this mean is, see, what is the significance of this? If you want to understand, guys, you have to concentrate, okay? Try to understand what that means. What does this root mean? Look at that and look at this. This 5,
Are those still related since you took that S away? Oh, now this is a transfer function. Okay.
so look at that and look at this 5, okay? Does this have any impact on the response? As time progresses, this does not have any impact on the response. It's not driving. There is something constant about this. This does not change. Right? How does this 5 contribute to this response?
It's like kind of like a magnification.
The magnification, or the greater this number, the faster the decay. Got it?
The greater that, like
This
that.
number, this root, so So this root is directly related to this 5. Okay? This e to the power of minus 5 is a direct consequence of this. Okay? The greater this number, the decay, faster the decay. Alright? That's how this impacts. So what this means is, if you're looking at something, if you're looking at the spring mass damper system, if you want to stop it very fast, you design your system such that this 5 is large. Okay? Is it, let's think again. Right, so this is the significance of this root. Okay? Everybody understands that? Is it clear? Why do poles, what do poles mean?
So, yes.
Poles are directly responsible for affecting the response. Okay? Yes.
Now, perhaps you erased it because you didn't want to discuss it, and that's fine, but the 0 was removed, right? But if we would have left that 0, how does that 0 relate to that transfer function right there?
So it's not a transfer function. 0 was because of what? Because of this input. Okay? 0 came because of this input. So,
But I'm saying, not transfer function, how does the 0 relate to that time response equation? Or is it not related like that -5 is?
So you have to understand something.
That would have been constant, right?
Huh?
That would have been constant.
That would have been a constant, but what we want to know here is, we're trying to understand poles and zeros regardless of the input, independent of the input. This input can change, correct? Input can be this, input can be a unit step input, input can be a ramp input can be a sinusoidal input, which you were seeing, you saw a sinusoidal input there, okay? When we define these poles and zeros, they are independent of that input. So this transfer function is independent of the input. Transfer function is defined independent of the input. Now if you have a system, if the system was itself like this, s plus 2 over s into s plus 5, this would be a second order system, okay? This would have, what impact would it have?
Well, in that one, 0 would be a root.
Huh?
In that one,
In that 0 would be a root, but that would not have a significant impact. It will only have a constant, it's like, your slope. If you look at the straight line, y is equal to mx plus c. What does that c give you? Does that c have, what impact does that c have? It just shifts the line, correct? The slope does not change because of that c. Does it change? So this thing, this just shifts. The shape remains the same. Because of this 0, this shifts. Okay? That what value? So if you had a here, let's say 2. So this will be different. This first will be different if you have that. This constant term will be different. So that just means it will just shift. The shape will remain the same. Okay? So poles of a transfer function are what? So roots of a denominator equal to poles of a transfer function. Okay? Let's always keep this in mind. And what would the zeros be? Roots of the numerator of transfer function. We have to keep in mind this of transfer function equal to 0 of a in other words, system is 0 and s equal to minus. Okay.
What does that mean?
So again, just look at this system. If you want the transfer function to be equal to 0, at what value of s would the transfer function be equal to 0? Huh? Yeah, that is a 0. That is called a 0. It's that simple. So roots of the denominator, poles, roots of the numerator are zeros. Okay. Now it so happens that these poles and zeros, if you think about frequency, you have to think about complex numbers. Okay? Frequency cannot be expressed in simple numbers. Do you remember complex numbers? Or how the representation of complex numbers?
It's on my eye.
Huh?
Eye, like imaginary.
Right. You remember a complex plane? No?
So, okay.
So you take it to reconsider G of S equal to S plus 2 divided by S plus 5. This can be written as, see, we use this representation pretty often.
Excuse me, Dr. Simon. Would you mind opening up the propulsion lab for me? My group is presenting first. I need to go present in the propulsion lab for design.
I don't remember the key off.
Oh.
I don't remember it off my head.
Well, where is it?
It's in my this thing. Just give me a second. So we'll finish this and I'll open the.
No, my group is going first at 9, so I don't have much time for me to set up over there. Sorry. Yeah, my group's, yeah. 6 and 9. Just a second.
I'll give you a second.
Can't see the thing. I don't see it though. I'll see it. I'll have something to look forward to. Completely disgusted.
I said even more.
Alright, just look at this. We'll just finish this and you can get going. So, if you have a system this is a mathematical representation. This is called the block diagram representation. Okay? It's very simple. You have a system here, right? As we have seen, this is the plant. This represents the plant. Okay? There is an input going into the plant, and then there is an output coming out of the plant. Alright? The plant itself has the transfer function s plus 2 over s plus 1. This is equivalent representation of this. Alright? Now, if you look at what are the poles of the system? Poles of the system are? Right. And s equal to negative 5. And 0 of the system are at s is equal to negative 2. Okay? So what you do is
Bless you.
you should know how to plot this. It's very simple. So you have, this is called the S is generally use this representation J omega. Okay? So sigma is this axis, which is the real axis. J omega is the imaginary axis. Instead of I, we use J. Okay? You understand why this could be the case, right? So mathematically think about it. The roots could be what? What are the three options for the root? The roots of the system can be
Positive, negative, imaginary, something like that.
right. So the roots of the system can be real and distinct. Roots of the system can be real and repeated. And roots of the system can be complex. Complex or imaginary.
Okay, so complex. What was the next one?
Imaginary.
I thought complex was imaginary.
Complex will have both real part and imaginary part. Okay? Imaginary will have only imaginary part.
Okay.
You said real and distinct, real and what?
Real and repeated. For example, s plus 2, the whole square, would be, that is real and repeated. So the roots are minus 2, and there are two of them. S plus 2 into s plus 3, the roots are plus minus 2 and minus 3. And you can have something complex. So s minus, for example, what is the root of s plus s minus 9? Okay, what are the roots of this? Or s square plus 9?
Minus 3.
Hmm?
Negative 3.
It's not negative here.
Yes, square root.
So s is equal to minus 9, root of minus 9, right?
Which is negative. Oh, 3i.
That is negative 3j. These use negative plus or minus 3j. Okay? This is a purely imaginary root. So when you plot this, here what are the roots? Roots are here, the 0 is simply minus 2. Okay? So you have 1, 2, 3, 4, 5. We use this notation to plot our 0. We use a 0 and a cross to plot our 4.
A 0 to plot a 0.
And then an X to plot.
X to plot the 4. So here, what is this? S is equal to negative 5. This is okay. So this is how you plot. This is called the S plane. This plot is called pole 0 plot. Very simple, nothing complicated. Okay. Given any roots, so how would you plot plus or minus 3j?
That would be on that J axis.
Right, so you have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So you will use minus 3j, plus 3j would be this,
Yeah.
minus 3j would be this. And complex and imaginary roots always exist in pairs. They will never exist in
But now
by
that-
itself.
Those would be circles, right?
Huh?
Yeah.
It depends on whether they are poles or zeros. Right? They will most often than not complex, they'll be poles. Okay? So we'll discuss that. But this is clear, right?
Yeah.
How to do the pole plot. This is the S plane, and you just look at the roots of the denominator, roots of the numerator, and then plot it on the pole 0 plot or S plane. This whole thing is called the pole 0 plot. We can stop here.